Welcome to the Unbalanced Fault Analysis video series, and this is the second part of the video series. In the first part of the video series, we have looked into the concept of symmetrical components, and we see how is a symmetrical components able to break down the unbalanced phase quantities into three balanced symmetrical components. And because each of the symmetrical component is balanced, we are able to apply the per phase analysis in each of them, just like what we have performed on the three-phase balanced fault analysis. And in this part of this video series, we will apply the symmetrical components onto various important components of the power network, and several conclusions is drawn from that later on. So let's start this video by applying the symmetrical component onto the transformer like what you are seeing right now. And for the transformer, we are not going too much into the details of it, but it is sufficient to know that the zero sequence, positive and the negative sequence impedance of the transformer are equal to each other, and that they all equals to the leakage impedance. Another thing we need to know is that the zero sequence circuit of the transformer is different depending on the connections of the diagram and whether or not the neutral of the transformer is grounded. Take for example, when we compare this transformer and this transformer, where both of them have their primary and the secondary being connected in the Y manner, but in this transformer, the secondary neutral is not grounded. In this transformer, the primary and the secondary neutral is grounded. When you have this sort of connections, then the zero sequence circuit will be a simple connections from the primary to the secondary side through the impedance, which is something similar to the positive and the negative sequence circuit of the transformer. But when you have this transformer, then the primary and the secondary is no longer connected and they become open circuit. And interestingly, when you have the Y and the delta connection like this, where in the Y connections the neutral is grounded, then the primary side is connected to ground through the impedance of the transformer. And of course, the impedance will be the zero impedance, but it doesn't matter because the zero, positive and the negative sequence impedance of the transformer are equal to each other. And just now we mentioned that this is similar to the positive and the negative sequence transformer, but I recall that in the three-phase balanced fault analysis video, we never consider what is the connections of the diagram when determining the equivalent circuit of the positive and the negative sequence transformer. And rightly so, because the positive and the negative sequence circuit of the transformer is not affected by the connections of the transformer. Next, we look into the applications of the symmetrical components on the Y-connected load. So this is the typical Y-connected load circuit, and this is the single line to ground voltage for each of the phase that we have derived. And the Zm over here represents the mutual impedance, and which also causes a voltage drop that we have to take into considerations, and this account for the Zm term, in each of these equation over here. Take the VA equation over here as an example. So VA is equals to Zs multiplied IA. This is the first voltage drop that contribute to VA, and then Zn In is also another voltage drop that contribute to VA, and then you also have the mutual impedance that contribute to the VA as well. So the Zm over here is due to the IB, and the Zm over here is due to the IC. So therefore you have this and this term over here, and similar logic can be applied on VB and VC. And notice as well that In is equals to IA plus IB and IC, and we can substitute In as such, and we can simplify and put that in the matrix form, and then look like this. And then this matrix form can be written in the more compact manner as such. So here to here is nothing complicated. So the phase quantity can be converted to the symmetrical component as such by multiplying the A matrix as established in the first part of the video series. And then we can rearrange these equations by multiplying A inverse on both sides of the equation, and then it looks like this. And then we have this unique term over here, A inverse Z, A, B, C, and A, which is what we call the Z012. And as you know, as X012 is equal to this, so the X012 is actually equals to A inverse matrix, multiply the ZABC, and multiply with the A matrix. So if you simplify this matrix, then it will look like this. And this can be further simplified into here by ignoring the mutual impedance. And this is something very important. Yeah, this actually tells us that the impedance of the zero, positive, and the negative sequence are independent of each other. Because they are independent of each other, we can say that the current in each phase will produce voltage drop of the same phase sequence only. And more importantly, because the impedance of each sequence is independent of each other, this allows us to perform our per phase analysis in each sequence, okay, without having them affecting each other. You can sort of imagine this by trying to determine what is the V012 by taking this Z multiplied with I. So when you want to multiply with I, then the I has to be the vertical vector with I0, I1, and I2. So when you go ahead and multiply this matrix and the vertical vector of the I012, you will realize that the multiplications, okay, like this, okay, if you can imagine, is not affected by each other. Okay, therefore, the voltage of zero, positive, and negative sequence is not affected by the impedance of the other sequence. So this is a very important property which allows us to apply our per phase analysis onto each sequence, okay, independently. Next, we also want to look into the applications of the symmetrical components on the Y-connected balance generator, and that the generator is also loaded. And because they are balanced, we can go ahead and say that the phase A, B, and C are 120 degrees apart from each other as such. Okay, recall that A is actually equals to 120 degree phase angle. A squared is 240 degree phase angle. And then we can also derive this equation, which is a simple voltage drop for phase A, B, and C. So take for example, in the derivations of this equation, we will walk through this circuit from here to here. As we arrive here, we will have a voltage drop of negative IAZS, and then we get positive EA, and then we get negative INZN, and then we get negative VA equals to 0, and we form a complete voltage drop. And then we rearrange the equations, we will obtain this form. And we can apply the same concept on phase B and phase C as well. And notice also that IN is equals to IA, B, and C, and we can substitute this one inside, rearrange the equation, and put them into matrix form, and they will look like this. And rewrite this into the compact manner, they will look like this. And we can convert this into the symmetrical component form by multiplying the A matrix like this. And then we can rearrange the equation by multiplying A inverse on both sides of the equations to eliminate the A, and then it will look like this. And recall that this is a unique form that we also obtain in the analysis of the Y-balanced load. And we also call this Z012 in this analysis. So because this and this are equal, I can write 012 in the matrix form like this. And I can simplify this equation, and the equation will look like this. Okay, and this is a very important quantities or property over here, which shows that the zero sequence impedance can only exist if the neutral is grounded. Okay, if you notice over here, Z0 can only exist if we have a Zn over here. Okay, that is when the neutral is grounded. If Zn does not exist, then Z0 does not exist anymore. So we can say that zero sequence current can flow only if the neutral is grounded. The take-home point between this analysis and this analysis is that the analysis of symmetrical components on a per phase basis is independent of each other, and that the zero sequence impedance can only exist if the neutral is grounded. So we are going to analyze the three-phase connected balance generator further, and then because they are balanced, we can say that the zero sequence and the negative sequence component of the generator are zero. In fact, this is a very important property that we normally ignore in the analysis of the balance system, as well as in all the circuit analysis that you have learned in the circuit analysis. in those balanced system, by default, we are actually performing the analysis on the positive sequence, yeah, because the zero sequence and the negative sequence components are 0. And then we can go ahead and apply this one into the previously established relationship as such. Okay, EA012, we can substitute this one with this, and then it will look like this. And then we can expand this one and rewrite this one into each of their sequence as such. And from this, we can establish these simple circuits over here. Take, for example, the positive sequence. VA is equals to EA minus Z1IA1. So this one is represented as this simple circuit. EA minus this is equals to this, right? This is a simple voltage drop that you know. So VA0 is equals to negative Z0IA0. So VA0 is equals to 0 over here. You have nothing over here. Minus this equals to this. Okay. Similarly to VA2. 0 minus Z2 IA2. Yeah, not square, is the negative sequence 2, yeah, equals to VA2. So 0 minus this equals this. And what is the observations that we can observe from here? There are 3 observations. The first is that the positive sequence is the same one-line diagram used in studying the 3-phase balanced currents and voltage. Okay, notice over here. So this is something that we are all familiar with, and this is something that we normally apply in our balanced system. And the positive sequence network has a voltage source, therefore only this network has a positive sequence voltage drop. Okay, so this is quite obvious. Because only this one has a voltage source, therefore you only have voltage drop over here. And then the sequence system can be solved on a per phase basis, okay, because if we are able to establish this and redraw this into 3 separate circuits, we are able to analyze each of these circuits separately, and due to this, we can say that we can analyze our sequence separately as well on a per phase basis. So this is the end of the second part of the video series, where we have looked into the applications of the symmetrical components onto the analysis of transformer, Y-balanced load, and Y-balanced generator. In the third and final part of this video series, we will then combine what we have learned in this video and also the concept of symmetrical components into the analysis of various unbalanced faults. And then the concept will look more clear, and then they will all come together. But before we go into that video series, take your time to familiarize yourself again with the symmetrical component concept, how you are able to break down unbalanced phase quantity into symmetrical components, and that you have to be very comfortable in handling the conversions between phase quantities and symmetrical components. And also take your time to try to go through the derivations of the applications of the symmetrical components in the transformer, Y-balanced load, and also the Y-balanced generator. And thank you for listening, and I will see you in the third part of the video series.